Hi again everyone, Chris Tisdell here again. In this presentation I'm going to continue my series of videos on vectors. Now in previous videos we learned about a new way to multiply two vectors together called the dot product. And when we take one vector and dot it with another vector, we get a number, not a vector, as our answer. Now I'm going to build on this idea of the dot product a little bit more in this particular presentation, and I'm going to talk about the angle between two vectors and introduce the idea of orthogonality. Okay, so let me share my screen with you and I can show you what I mean. Okay, so just to refresh our memories, the dot product is just a special operation between two vectors where you multiply the corresponding components together and you add up all the multiplications. Okay, and I showed you, and I gave a proof of this, that we can connect this dot product with the lengths of the two vectors involved and the angle between them. So you might have, say, a vector A here and a vector B there, and theta is the angle between them. Okay. Now, I'm going to build on this idea a little bit more in this presentation, and it's contained in the following slide. So we know that we can use this dot product to compute the angle theta between two vectors. Now, if the angle between two vectors is pi on 2 or 90 degrees, then we say the two vectors are perpendicular to each other, or normal to each other, or orthogonal. Okay, all those terms are kind of interchangeable. All right, so you might have, say, a vector here, B, and say a vector A here. You can see that the angle between those two vectors is pi on 2 radians, and you would conclude that, oh, okay, those two vectors are orthogonal. Okay, or you could have a vector going like this and a vector going like this, and they'd also be orthogonal. Or you can have a vector like this and a vector like this, and they'd also be orthogonal. Okay, all right. Well, if we combine this concept with this idea of orthogonality, we can make the following conclusion, right? Let's say I've got two vectors A and B, and I compute the dot product of those two vectors, and the dot product turns out to be 0. Well, if the dot product's 0, then the angle theta between the two vectors is pi on 2, and we would conclude then that A and B are orthogonal, normal, or perpendicular to each other. So let me show you where this comes from, and see how we can make that conclusion. Let's say the dot product is 0. Then, from this relationship here, we know that the cosine of the angle between the two vectors is just the dot product divided by the product of the lengths. Okay, well, if that's 0, then this numerator is 0. So this is just 0. Okay, so we know that cosine theta equals 0. And in this setting, the theta is always between 0 and pi. Well, there's only one value of theta that will satisfy both of these two things. It's the value pi on 2, or 90 degrees. Okay, so that's why this is an excellent test for orthogonality. Okay, if you take the dot product and the dot product 0, then you know the two vectors involved must be perpendicular, orthogonal, or normal to each other. Okay, so let's talk about this a little bit more. Let's talk about an example. If I take, say, A to be the unit vector I, so let's say we're working in R squared, and let's say B is the vector J, which is just 0, 1, then you can work out that the dot product of these two vectors, well, it's 1 times 0 plus 0 times 1. So these vectors are orthogonal. Okay, and you know, we know that anyway because we know how to draw in these vectors, right? The I vector is here, and the j vector is here. Well, I've drawn in the x and y axes here. Okay. All right. So I'll do a little bit more through an example on this orthogonality a bit later, but I wanted to take this one step further. The idea of orthonormal vectors. Okay. So this is getting a little bit more complicated now. If we combine the idea of orthogonality with the idea of unit length, okay, then we arrive at the concept of orthonormality. Okay, when I say unit length, I mean vectors having length or magnitude equal to 1. Okay, so what is the definition? Well, let A and B, say, be two vectors. If their dot product is 0 and the lengths of the vectors are both equal to 1, then we call the pair of vectors an orthonormal set. Okay, so let me go back to the example that I had on this page. We had the I vector and the j vector. Those two vectors are definitely perpendicular to each other or orthogonal, and we know that I and j both have length equal to 1. So this set here, I comma j, would be an orthonormal set. Okay, and the idea generalizes. This is the most basic idea of a set of orthonormal vectors, where you have two vectors in your set. What happens if you have three vectors? Well, you can have as many vectors as you like. Okay, so let's look at a set of three vectors, I, j, and k in three-dimensional space. Each of these vectors have length 1, and they're orthogonal to each other because I dotted with j equals 0, I dotted with k equals 0, and j dotted with k equals 0. Okay, but let's look at some sets that aren't orthonormal. Okay, why isn't this set orthonormal? Each of the vectors have length 1, so that's, you know, that unit length property is satisfied. But this vector and this vector, the I and the negative I, are not orthogonal because they point in opposite directions. So there'd be an angle of pi radians between these two vectors. So that is not orthogonal, because an orthonormal set, because these two vectors are not orthogonal. What about this set here? Is that an orthonormal set? Well, each of the vectors are orthogonal to each other, but this vector 2j doesn't have unit length or length equal to 1 because it has length equal to 2. Okay, so that's a little bit about orthonormal vectors. Let's try to bring everything together in an example. Okay, determine whether or not the following set forms an orthonormal set of vectors. Okay, I've just used S to denote the set. All right, so what we want to do is check to see whether or not each of these vectors have length 1 and they're all orthogonal to each other. Okay, so we ask our question, are the vectors orthogonal to each other. Okay, so let's look at the dot product. Let's call this, say, V1, V2, and V3. V1 dotted with V2. Okay, so it's 3/5 times 0 plus 0 times 1 plus 4/5 times 0. Okay. So that just gives 3 lots of 0, which is 0. Okay, let's work out the dot product of, say, V1 with V3. Okay, 3/5 minus times negative 3/5, so that's negative 9 on 25. 0 times 0 plus this. Okay, so what do we get here? We get something like 7 on 25. So we can say that actually, because this isn't 0, this is definitely, V1 and V3 are definitely not perpendicular to each other. Okay? So we can actually stop now. We can say these two vectors are not orthogonal to each other, and therefore the set cannot be an orthonormal set. Okay? Now, if these two components were switched around, let's say I had a negative 4 on 5 up there, and a 3 on 5 down here, would that form an orthonormal set? So I'm going to give you an exercise to do. Let, I don't know, S bar be the following. So let's say it's pretty much the same set. Is that set orthonormal? Okay, so that set's definitely not orthonormal, but I'm asking you to think about this form. Okay, is this set an orthonormal set? Okay, so if you have answers or questions, post them in the comments section. Okay, so that's a little bit about orthogonal vectors and orthonormal sets. Okay, in forthcoming videos, we'll be looking at how we can use the dot product to measure projections and distances between, say, points and lines. Please join me for those presentations, and if you have any questions, any comments, any feedback at all, just put them in the comments section. So thanks for watching. Join me again for my next presentation. Bye.